Hello everyone, my name's Jory and my partner's name is Giovanni, and today we're going to be talking about beating the odds in the NBA using machine learning. First, we're going to start out with a general introduction to sports betting, since I'm sure most of you probably aren't familiar with how this works. So, what is fixed odds betting? Fixed odds betting is the traditional form of betting where you predict what's going to happen in a sports event and then place a wager on your prediction. The odds are agreed upon when the bet is placed. If the bet wins, the payout is based on those agreed odds. In a sports wager, there are always two parties, each one essentially taking an opposing view to the other. While betting amongst friends is common, we're going to focus on betting with a bookmaker. And books are becoming more and more popular across America. I don't know if any of you have heard of DraftKings or FanDuel, but those are very popular websites and companies where you can place bets. Sports betting is growing in popularity, with the global sports betting market size expected to reach $140 billion by 2028. Because we're going to be focusing on bets that one person makes with the bookie, we're going to talk a little bit about the bookie versus bettor relationship. And one could definitely describe this relationship as a rivalry. Both parties are after the same goal, which is essentially to create a model that can predict the outcome of a sports event with perfect precision. This is extremely difficult, and we know that the outcomes of lots of sports events are random. However, in order to find value in the sports betting market, we need to assume that it is inefficient, meaning that the betting line may not reflect all of the available information in the game. Or, in other words, something that we can figure out that Vegas maybe hasn't put the time or money toward that we can make money off of. So here you can see the different kind of proposition bets in the NBA that one might place. Some examples are amount of points scored, total assists, total three-point field goals, or total rebounds, which is what we decided to focus on. If you look underneath every example, there is a little chart that will show you what you would see on a book. And those over and under bets, next to it is the odds of the bet hitting over or under the value shown above. These are American odds, and they can be converted into normal probability odds that would be compared to our model. So just to give a little background on rebounds, a rebound technically is the retrieval of the basketball after a missed shot. Here you can see the distribution of rebounds in the NBA, and what's very interesting about rebounds, which is why we wanted to predict rebounds, is that every missed shot in the NBA provides a chance to rebound for both offensive players and defensive players.
I will now talk about how we produced and pre-processed our data. The original data set we began with contained box scores on every regular season game for the past 5 seasons. This means that each row contained one player's statistics from a certain game. To avoid look-ahead bias or using statistics from a certain game to predict other statistics in that same game, we created columns that contained the respective player's statistics over the past few games. After this, we added teams, odds, player weights, player heights, and player positions to the data set in an effort to include more features that we thought would be explanatory of rebounds. This resulted in a data set with over 50,000 samples and 42 features. We used one-hot encoding to convert player positions into binary variables, and we also normalized our numeric features in order to weigh them equally in our model cost functions. After this, we used a Pearson correlation heat map to uncover any multicollinearity among our features. With each pair of highly correlated features, we chose to remove the one that was less correlated with rebounds. The correlation of each feature with rebounds in particular can be seen on the right. Removing just a few features fixed most of our multicollinearity, and that is illustrated by the updated heat map on the left. We then fit a simple linear regression model to our pre-processed data, and we were able to achieve an R-squared score of 0.4. A scatter plot of the real rebounds versus our predicted rebounds can be seen on the right. Next, we tested out a few more complex models. The models we ran were ridge regression, gradient boosting machine, random forest, and a neural network. We used k-fold cross-validation to find the optimal hyperparameters for each model. A bar chart of the preliminary results can be seen here. We were able to achieve our highest R-squared score of 0.419 with the gradient boosting machine. Eventually, we were looking to incorporate our predictions into a betting strategy by backtesting the profitability of our predictions against Vegas's rebound odds. Thank you for listening to our presentation, and we hope you found it interesting. Have a great day.